hand over to
Oliver. As you start sharing your screen, it will be my pleasure to introduce Oliver Brock. And just a quick notion. Frederick, you got many questions. I don't think we will have the time to cover all of them. You may want to start answering some by chat. So yeah, it's really my pleasure to introduce Oliver Brock. Oliver started by looking at how to navigate safely a robot in space, and very quickly found out probably that navigating it without an arm on it was not very interesting. So he moved on to navigating while manipulating, which is still a very open problem in robotics. Of late, and I guess this is what he will present to us, he did extremely interesting work on both the hardware side of manipulation to design new robots that are flexible and soft, but also to look at how this softness and actuation could be used also as a way of perception, of perceiving the contact. And he has also reminded us of how important it is when you're doing manipulation to take into account the context, that you may use the environment to actually help you manipulate objects. And most recently, he's been looking also at how to reduce the sheer dimensionality of manipulation. And I guess this is what he will talk about in this talk.
Yeah, hello everybody. Thank you very much, Aude, for the introduction. Yeah, I'm going to talk about, well, let me start with a comment that Aude made all the way in the beginning in the introduction to the workshop. And she said that we cannot hard code everything, and therefore it's obvious that we need learning. And I very much agree with this. But basically what my talk is about is exactly where this boundary falls between hard coding and learning. And maybe to start off our discussion, I would like to take a look at a system that very much comes from one extreme of this spectrum, which very much focuses on machine learning. Before I play the video, just briefly, I would like to point out that this paper has 18 authors. Right, just to give you some idea of the amount of resources that was behind this. These authors took 2.5 years to write this paper. They had 100 of the fanciest GPUs, so that doesn't sound like much, but it actually is, between $500,000 and $1 million worth of equipment. And they also had about 32,000 CPU cores, which is about 10 times as much as my lab has. Altogether, they then basically simulated 13,000 years of manipulation experience. And that was basically the training data needed to show what I'm going to show you now, which probably most of you have seen. And in doing so, they actually basically designed away most of the perception problem, and I will get back to this later, they used an off-the-shelf hand whose design objective was to mimic the degrees of freedom of the system from the human hand. So just very briefly to show you what this hand can do, and it's clearly a very, very impressive demonstration of in-hand manipulation. You might wonder why the hand is wobbling like this. At least I'm wondering. And if you look closely, you actually see that the hand kind of gets stuck. This rotation is very nice of the top row, but the next one actually gets stuck. I'm not gonna show you the whole thing. But my point really is exclusively that they used a tremendous amount of resources to facilitate machine learning and to solve this particular problem here. By the way, if you just want to solve this particular problem, here's a video of the world record. I'm not sure if Zoom can do this because it actually just takes 0.6 seconds of solving this cube. So if you wanted to engineer the system, this is what you could do. But so why do I think it's a problem that they just took an off-the-shelf hand? I think it's a problem because if you want to design a system, all the individual components need to fit with each other. And so by taking a particular hand that maybe doesn't fit their learning approach, they might make that problem unnecessarily difficult. This point is so important to my talk that I want to illustrate it with a piece of art, actually. This is a guy I know, Julius Popp, who's an artist. It's a piece of work that's already 12 years old. It's a bad quality video. So what you're seeing here is a bunch of transparent tubes that are sort of lying on the floor. And sound you hear is valves that are clicking on and off. And you can see that in the middle, these little red bars come together and look like letters. To relieve the suspense, it actually spells out there may be coup, which was a headline in 2008 about a coup in Guinea. But as these letters progress into the rest of these tubes, you see that information kind of disappear. Obviously, the information is still there, but things become very complicated, and it will be very difficult to extract the information from any other region than this one, right? So I would argue that if we want to do manipulation and in-hand manipulation, we want to be somewhere within that red circle. We want to be where all the pieces are aligned in such a way that the system and the problem becomes simple. And I guess this is kind of the motivation for most of the research that my lab has done in the past in manipulation. And we started very much aligned with the goals of this workshop by looking at humans and studying how they grasp. An outcome of this can be seen here, where we've taken the insights that we've gleaned from humans and ported them into robotic strategies, where here maybe as a first step to pick up a ball, you would do visual servoing. You would servo then the hand here, a Barrett hand, to the table surface. You would slide the fingers along the table surface until you touch the ball, and then you close your hands around the ball. So as Odd already mentioned, this is kind of a little bit of a different view from, let me see if I can get rid of this window here with all of you so I can actually see. Actually, I can't. The idea here is that only at the very end, only in step 4, do we actually reach something that resembles force closure. Everything else is dynamic, is motion, is temporally extended, and really exploits, as Odd was mentioning, the environment. So we can view all of these things here as funnels. I'm just going to give you one example. In the beginning here, we have visual servoing, and visual servoing basically provides some kind of field for us to get to a place that's indicated by the red ball, which is sort of the end of the funnel. Or if you want here, the table surface provides the wall of the funnel, whereas the red ball is here at the bottom of the funnel, stopping the motion. So we're using the environment and the object to simplify control problems and to outsource aspects of perception to the interaction between the hand and the environment. And so these funnels here are really the basic entity that I would like to propagate as a low-dimensional representation for machine learning. So we should learn both these funnels and how to compose them. But I want to talk about these funnels in more detail. Just a quick video of what happens sort of in a traditional sense. Here you see a robot picking up a piece of paper, a little entry ticket or business card from a table using these extensive environmental contexts. And you can see that this is robust and elegant. But I want to talk about really in-hand manipulation here. And I would claim that in-hand manipulation and grasping and manipulation sort of all collapse in this view of funnels, where we're trying to find funnels that are supported by features in the environment. So here's an example of our hand. This is the RBO hand 3, which is actually still unpublished, but it's the most recent hand that we have, performing some kind of very simple in-hand manipulation. And it's kind of difficult to see which part of the hand is actuated and which is not. It actually was just the index finger and the little finger. Everything else was passive. So basically in this case, in in-hand manipulation, it's the hand itself that provides both actuation as well as aspects of the environment. The hand is the environment that provides these constraints that we can exploit in these funnels. And if we want to do dexterous, competent in-hand manipulation, the hand needs to be able to reconfigure itself to provide all kinds of different types of constraints. And so we've designed the hand to be much more dexterous than our previous hand, the RBO hand 2, Each finger now has 2 degrees of freedom that mimic basically kind of the degrees of freedom of the human hand. You can spread the fingers, which is important for in-hand manipulation. You can actually bend the palm. And obviously, as with any hand, the thumb is a key component, and it needs to be opposable, which is here tested in a Kapanji test. So you can see that this hand is much more dexterous, and thus we hope we'll be able to really provide a test bed that can generate an environment for an object that can both provide actuation as well as constraints. The 2 people that have built this hand are Stefan Puhlmann and Jason Harris. But I want to, like I said, talk about in-hand manipulation, and I want to show you this little video here of the RBO Hand 3 performing in-hand manipulation. You see here two sliders. The first slider, the top slider, actuates this degree of freedom here, which is a rotation, and the second one actuates this degree of freedom, which is bending of the finger. And so you can see that basically just by actuating the thumb and nothing else, you can see that that this finger here actually performs a pretty wide motion to respond to the motion of the thumb, thus rolling this object in hand. You could view this as one of the possible funnels of in-hand manipulation. And clearly this is one human-controlled experiment. If I want to claim that this is a general approach to look for these funnels, we need to show that this is generalizable, so it works with multiple objects, it's robust, it works repeatably, and it's composable. And so this is what I would like to show. First of all, I would like to say this is Aditya who has done this work. He's not 13,000 years old, so his experience is much less than the experience that OpenAI could gather. And actually, he's just a beginning PhD who in his previous job didn't actually work with real robots, so he's somewhat, well, I wouldn't say unexperienced, but he has not worked with these hands before. So here's a particular funnel that he developed. Yeah, I'm just going to play this to show you that we can sort of rotate this cube in hand 90 degrees with a very simple routine and then push it back to its initial position. Now I can show you the same thing it's exactly the same program. It's exactly the same. It's an open loop actuation pattern of the hand with a totally different cube, different size, different weight, different surface properties. And the exact same thing works also here. So clearly this is not conclusive evidence, but this is all, these are all experiments gathered within the last 48 hours. So I guess this is really showing you work in progress. Now, let me also show you that we can sequence these things. So here you see the original wood cube. I'm going to show you something that Aditya did, where first of all, this cube is going to be flipped to be closer to the fingertips. It's going to be rotated and then going to be pushed back. This is going to repeat twice. Then it's going to be restored to this original hand location, and then this program is going to be executed twice. So you see here the consecutive execution double nested of an open loop program for in-hand manipulation.
12 minutes.
So this is first bringing it into this position. Now it's rotating it, pushing it back to the original position. And now this interior loop repeats where it's flipping this by 90 degrees and pushing it back to the original place. Now it's going to restore the original position. And you can see that it's not actually really restoring the original position. There are significant errors and displacements, but still the second execution of the exact same program works in exactly the same way. So first it's being moved to the tip of the fingers, it's being rotated by 90 degrees, and it's being restored to the previous thing. You see here now there's a very different angle that this object is taking, that the cube is taking. And there is again the flip, which is followed again by the restoring movement. Just to show you that this is actually the program, these these reset actions here are only there because there's a leak in one of the actuators, and so we need to reset the air pressure. But other than this, this is a program that is showing that we can sequence these. I'm showing you a different recording of exactly the same program, that we can sequence these very simple funnels. We can loop them, and the program that we're doing here becomes very simple. Mind you, this is entirely open loop, and it's the compliance of the hand and the robustness of the actual primitive that provides the robustness so that we can repeat and loop these things. So I'm already coming to the conclusion. I wanted to make the point that basically all kinds of manipulation can be viewed as such a sequence of exploiting constraints. These constraints can be provided by the environment, or they can be provided by the hand itself. And if all constraints are provided by the hand itself, then we call things in-hand manipulation. But to me, really, in-hand manipulation and grasping end up being exactly the same thing in this view. It's the sequencing of funnels that exploit constraints. So the second point I wanted to make is that really we need to be looking for these funnels, because these funnels derive from geometry, they derive from material properties, they most importantly also derive from the design of the hand. And maybe now it becomes clear why I think just picking a particular hand and then trying to solve a manipulation problem is not the right way to go. We need to co-design the hand and the approach that we use to solving it. In our hand, the RBON3 has been exclusively optimized for the ability to exploit environmental constraints. And so then we need to be aware that the behavior of the hand that is indicated by this picture on the right is really the composition of perception, control, and planning, which is here, right? Which is the part, oops, sorry. Which is the part that that this defines what the actuation command is that we send. And then the rest is augmented, or this actuation command is augmented by the interaction between environment, hand, and object through contact, exploiting compliance, and exploiting constraints, hence 3 Cs. And together this interaction actually performs some computation, a 4th C, that modifies the behavior that we have computed explicitly in order to make things robust. So this interaction here is a second component, and we need to design these two things together, and we need to understand this interaction so that we can actually start solving difficult manipulation and in-hand manipulation problems. Thank you very much.
Thank you very much, Oliver.